Okay, have you ever thought about just taking the raw electricity pouring out of your living room wall outlet and plugging your $1,000 smartphone directly into it? No? Good. Because if you actually tried this without the bulky charging brick, your incredibly sophisticated, highly sensitive device wouldn't just fail to charge. No, it would fry instantly. Poof, game over. But why? Why is the electricity in our walls fundamentally totally incompatible with a supercomputer sitting right in our pockets? Well, let's dive into this, because the answer involves this fascinating, completely hidden world of electronic engineering that works tirelessly every single time you plug something in. Welcome to This Explainer. Today, we're zeroing in on a brilliant piece of technology that you use dozens of times a day, yet probably never even think about. It's called the rectifier. It's the absolute invisible power hero living inside every single charger, television, and computer you own. Honestly, without it, our modern digital age simply wouldn't exist. To understand how it works, we're going to walk through the evolutionary roadmap. First, the power problem. 2, the halfway fix. 3, center-tapped full-wave rectifiers. 4, the bridge rectifier. And 5, smoothing out the pulses. Let's jump right into part 1, the power problem. Alternating current versus direct current. So here is the fundamental clash we're dealing with. The electricity delivered to our homes by the power company is alternating current, or AC. Kind of like the tide of an ocean. AC periodically reverses direction. It sloshes back and forth. And hey, it's absolutely fantastic for traveling incredibly long distances over power lines without losing much energy. But here's the big problem. The microchips, the batteries, and the delicate motherboards in your devices absolutely despise the sloshing. They demand direct current, or DC. DC flows steadily in exactly one single direction. Feeding AC into a DC device is kind of like trying to drive a car by violently throwing the transmission from drive to reverse 50 times a second. It just breaks the whole system. So, enter the rectifier. This is an electrical circuit specifically designed to convert that chaotic, reversing, alternating current into the smooth, one-way, direct current that your devices crave. The rectifier is essentially the ultimate translator. It bridges the incompatible gap between the aggressive wall power and the delicate electronics on your desk. But how exactly does it force alternating current to just go one way? Which brings us to part 2, the halfway fix, a simple, basic solution. The beautifully simple half-wave rectifier uses just a single component called a diode. You can think of a diode as, well, an uncompromising nightclub bouncer, or maybe a one-way turnstile. So in phase 1, as the alternating current surges forward in the positive direction, our turnstile diode happily lets it pass right through. But in phase 2, when the AC tries to reverse direction and flow backwards, that's the negative half cycle, the diode literally slams the door shut. It completely blocks the reverse flow. So at the end of the day, you're only letting the forward-moving half of the electricity through. So what's the actual result of only letting half the power through? Well, technically speaking, yeah, you've created direct current. The electricity is now only flowing in one direction. But look at what it actually produces. The output is a highly pulsating DC. Because you completely blocked the entire backwards half of the wave, you're left with massive empty gaps in your power supply. It's essentially turning the power on, then off, then on, then off. This creates a highly inefficient, totally choppy power flow with a massive ripple factor. Because of all those empty gaps where the power was blocked, the maximum theoretical efficiency of a half-wave rectifier is an incredibly low 40.6%. I mean, you are literally throwing away more than half of your potential power. Because it's so incredibly inefficient, you are never going to see a half-wave rectifier powering a laptop or a TV. Today, it's strictly reserved for very cheap, low-power applications where supply quality really doesn't matter much at all, like simple signal peak detectors. But for anything meaningful, engineers knew they somehow had to capture that lost half of the wave. Moving on to part 3, center-tapped full-wave rectifiers, capturing that missing gap. Right, so if one diode only captures half the wave, the completely logical next step is to use 2 diodes. But to make that work, this design utilizes a very special transformer. Right in the middle of this transformer's wiring is a center tap. It's basically a wire that acts as a strict 0-volt reference point, effectively splitting the alternating current right in two. Now, during the positive surge of the AC wave, the first diode conducts the electricity. But when the AC reverses into its negative surge, instead of blocking it entirely like before, the current is routed through the second diode, which completely flips it to flow in the forward direction. The result? A continuous, back-to-back series of DC pulses. The empty gaps are totally gone. We have successfully captured the full wave. Now for part 4, the bridge rectifier, the absolute modern champion. Now, it is absolutely crucial to understand why that center tap design had to evolve. That center tap transformer we just talked about, well, it's heavy. It's physically really bulky. And worst of all for mass manufacturing, it is super expensive. When you're trying to build incredibly sleek, lightweight phone chargers or super thin flat-screen TVs, a giant metal transformer is pretty much your worst enemy. So enter the bridge rectifier. But utilizing exactly 4 diodes arranged in a really specific closed-loop bridge, engineers found a way to achieve that full-wave rectification without needing that bulky center-topped transformer at all. These 4 diodes operate in a highly choreographed dance, and they work in pairs. During the positive half-cycle of the AC wall power, 2 diagonally opposite diodes open up and conduct the electricity, steering it safely to the device. But when the AC violently reverses into its negative half-cycle, those first 2 diodes slam shut, and the other 2 diagonal diodes instantly open up. They catch that reverse flow and route it so it comes out in the exact same forward direction. So no matter which way the wall pushes or pulls the electricity, this beautifully elegant closed-loop bridge literally forces the current to exit flowing exactly one way. And just look at the result. The maximum theoretical efficiency shoots straight up to 81.2%. That is exactly double the efficiency of the basic half-wave rectifier we looked at earlier. Plus, because the pulses are continuous without any gaps, the ripple factor is significantly lower. We're capturing almost all the energy, and we're doing it in this tiny, super lightweight, inexpensive little package. So, to quickly summarize our evolutionary journey so far, we started with the half-wave rectifier. It's cheap, sure, but with terrible low power, making it pretty much useless for modern devices. Then we arrived at the full-wave bridge rectifier. High efficiency, low ripple, cheap to produce without those bulky transformers. It's really no wonder this is the absolute industry standard. Whenever you plug in a power supply for your computer, your flat-screen TV, or that little tiny charging block for your smartphone, you are relying on a bridge rectifier to do the heavy lifting of taming that wild AC wall power.
Okay, finally, part 5, smoothing out the pulses, the filter circuit.
But even at a magnificent 81.2% efficiency, we still have a bit of a problem. The bridge rectifier gives us continuous DC, meaning the electricity is definitely only flowing in one direction. But it's still doing it in pulses. It looks like a series of hills on a graph, bumping up and down really rapidly. If you were to feed that bumpy, pulsating DC directly into the delicate microprocessor of your laptop motherboard, the constant voltage spikes and dips would cause it to crash almost instantly. It absolutely needs perfectly steady, unwavering power. So we add the final piece of the puzzle, the filter circuit. Right after the power leaves the bridge rectifier, it passes through components called capacitors and inductors. You can basically think of a capacitor like a magical electrical sponge. When the pulse of the rectifier output rises to its peak, the sponge soaks up the extra electricity. Then, just a tiny fraction of a second later, as that pulse starts to dip down into a valley, the sponge automatically squeezes out its stored energy to fill in the gap. It completely irons out those bumpy hills and valleys. The end result is this perfectly smooth, completely flat line of direct current that safely and beautifully powers up your most sensitive devices. So the very next time you casually plug in your phone, just take a second to appreciate the incredible journey that electricity just took. It was caught from a sloshing, chaotic AC wave, expertly steered through a microscopic one-way bridge of diodes, and meticulously ironed out by a sponge-like filter circuit, all in a fraction of a single millisecond. Seriously, take a look around you right now. How many hidden bridge rectifiers do you think are silently taming the electrical chaos in your room at this very moment? It's a beautifully complex world hidden right inside your wall sockets. Thanks for exploring it with me, and definitely keep questioning how the invisible things around you actually work.